Good afternoon, everybody. Thank you, Barbara. These are some of the first results of a project that was funded on the National Strategy for Sustainable Development by the Ministry of Environment, and this is a joint project of University of Florence and IRPET, as you can see, but also ISTAT is involved quite largely as some member of the ISTA staff are included in our unit of research, so we were able also to access some new data to develop the model. How to go? Okay, great. I skip directly to the background. Our work can be, if you want, included in a literature stream about the water footprint debate. And essentially, I simplify a lot, but you can find two different positions in this debate. The first one is a position that based the concept of water footprint as a volumetric one. And the idea is that the problem of water scarcity is a global one, so you have to optimize at the global level the use of water. On the other side, a stream of literature from life cycle assessment field of studies support a different vision in which the water use should be in some way weighted according to the environmental relevance of the use. So the idea is that in a water-rich region, if you remain under some given level, you do not harm the environment with the use, because water is a renewable, partially renewable resource. So they weight in some different way the water use. What we do, our approach in some way is between the two. We are developing an environmentally extended input-output model for Tuscany. And our model obviously generates a comprehensive accounting framework for water flows between economic activities and water bodies. In this sense, this is water use in a volumetric sense. So we quantify the million of cubic meters used by the economy. On the other side, we use this measure against the availability. So we model the pressures on water as in the LSE approach. The input-output structure of our model obviously allows us to model the implicit water flows between sectors and regions. And furthermore, we include also modeling the natural variability of the hydrological system in some way to include also an assessment of risks in the generation of water pressures. What are the innovative features we are trying to develop? First of all, we do not consider simply the net demand for water, so withdrawals minus the discharge in the environment of water, but we include also the gray water consumption. That means that part of water that is needed to maintain at a given quality level the water bodies. That in some way, if economic activities discharge water at a lower quality level than the minimum one, if you want, you need in some way immobilize some part of the natural stream that is no longer available for use because you need to maintain a given quality level. Our water supply is not the natural one, but includes also environmental constraints. So we, in some way, consider the environmental relevance of pressures. And finally, in the variability of water demand and supply, we include also some endogenous components in the sense that there are some linkages between water supply and water use. For example, agriculture in a low rain year increase the water demand for irrigation. So they do not vary in an independent way. There are some endogeneity that have to be modeled. The logical structure of the model is an environmental extended input-output model. So we have the economic system that withdraws water from water bodies and discharge water. Wastewater sometimes need to be treated to become again restituted to the environment to be again used to the hydrological system, and there is the recharge of the hydrological system. So all these flows are in some way modeled in our model. So the net demand for us is withdrawals minus discharges. But the extended demand, that is the demand for water we consider, is net demand plus water for dilution. And in this presentation, we will show the first potentiality of an input-output model, that is reclassifying the demand, the first round of demand, because obviously in the economy, there are some sectors that actually withdraw directly from water bodies, water. Other one that use water, purchasing them from other ones. So, for example, the water supply industry sell water to not only to final consumption, but also, for example, to all the greater part of service activities that, in some way, in indirect way, demand for pressures on the water bodies. These concepts are applied to each economic sector, and we disaggregated also the model among the local labor systems that are sub-regional areas with that in some way makes sense from an economic point of view, self-containing the largest part of the work market, so where people commute for working and living. So at the end, the model includes, at the center of the model, there is an interregional input-output model with 53 sectors in each of the 49 local labor systems. So highly detailed table. The table is implemented and integrated with some physical accounts of flows from and to the water bodies and the economic activities. So we have on one side the rows of withdrawals from 3 different water bodies, actually surface, ground, and rainfall. We included, for completeness of the accounts, also the natural cycle, hydrological cycle, even though the pressures are measured only on available supply of water that are groundwater and surface water. And on the other side, we have the columns of the 3 water bodies for accounting for discharge. You see in the bottom of the slide 3 coefficients. So we quantified for each economic activity and each local labor system a coefficient that is a ratio of withdrawals or restitution divided by the by 1 unit of output measured in euro. Okay, a great effort was also to disaggregate and assign to each sector labor system also a coefficient estimating the quantity of water asked for dilution, so for maintaining the quality of water in water bodies. I skip quite, this is a standard input-output extended model, so the extended demand depends from the economic activity, so we can in some way simulate changes in the vector y of final consumption to simulate changes in the pressures on the extended demand of water, and the S and C expression refer to the reclassification of the first round of impact from the extracting sector, such as agriculture, industry, or water supply sector, and using sector, so demanding sectors. just to get a reclassified extended demand in the economic system. This slide show, for example, what means changing, reclassifying the extraction. And you see that we have a sector that is sewerage, that it is a net negative withdrawal sector, in the sense that simply restitutes water arriving from final consumption and production activities. But if you reclassify, obviously this role is redistributed among the other activity. And you see also that agriculture is an important extractor of water, but the largest part is from rain. And on the other side, a large part of this direct demand is in some way transferred, sold to other sectors using agricultural products, mainly food industry and touristic activity, for example. In the table in the bottom of the slide, you can find some estimate, some figures about this, and you can see that we can estimate not only the average level, yearly in level, but also a coefficient of variation of this demand, this component of the demand for water. And this is the reclassification for the whole set of sectors at the regional level. So we are still talking about the regionally aggregated model. And you see, I don't know if you see in the bottom, but the first, on the left side, you have 8 sectors of agriculture, 12 and 13th, the 12th and the 13th sector are referring to food and beverage activities, and are indicated also the water supply and the sewerage. And you see what changes in terms of extended demand and reclassified extended demand. We model pressures on water resources, and our indicator, we call it EPRI, is the ratio between the extended demand, so that is different from the net demand, for example, used in the EU Water Exploitation Index, and the water supply. Our water supply is not a natural one, but a feasible one, and also this is the difference from the EU indicator. The supply consider environmental, technological, and institutional constraints. That means concession for the extraction, or the fact that there is a minimum flow runoff level for environmental purposes, or the fact that in some years economic activity would not be possible to use the whole runoff because we do not have enough, for example, facilities to storage water for productive uses. So these are the figures about the feasible supply that we estimated at the regional level. And this is the representation of the hydrological variability. And this is the cumulative probability to get a given level of the EPRI for the groundwater, for the surface water, and finally the total. What I could say in saying this slide is that if you look at the whole region, you feel that you are not in a so bad situation, in the sense that very improbable events, you get more than 30% of the feasible supply used by the extended demand. In general, it seems that, for example, 0.2 is in the literature considered a level with no particular harm on the environment if the use is used. So, and our indicator is more tight than the U1. So, in some way, we could say we are confident in Tuscany. We do not have so much problem of water, but we now we move to model the regional variability. So these are the local label systems, And we disaggregated all the flows and also modeled the different variability in different areas. And now we can get an idea. This is the feasible supply by local labor system, and you see that the pattern is not obviously similar in all the region. There are areas where there is a larger availability of water for productive use, and other with less availability. And this is the extended demand. Okay, we are close to conclude. The extended demand, what I want to show, to stress here is the fact that the extended demand obviously is mainly concentrated in the metropolitan area along the Arno Basin. But what it is interesting also to notice is that the risks, so the main variability of the demand is in another area where there is less supply. That is the southern part of the region. So finally, because the two maps refer to the average and the variation of the average, and you see that we have a problem of overexploitation in one side of the region, but we have a problem of risks overexploitation in other parts. Obviously, the pattern of utilization of water is completely different. The southern part is more concentrated on agriculture, while the manufacturing is mainly concentrated in the northern and central area of the region. How we are going to use the model? First of all, we want to complete the structural analysis of water pressures on water resources in Tuscany. We want to perform a complete decomposition of the implicit water requirement for final consumption. This is a typical application of this set of models, typologies of model, and also the implicit flows of water among the different areas of the region according to the exchange of intermediate inputs. We want to simulate, obviously, scenarios, and we can simulate both macroeconomic or typical economic scenarios, changes of final demand, but also changes in the environmental scenario, because we have the parameter to change in the variability, for example, and also changes in water policy. For example, we can model changes of rules about the maintenance of a given quality level in the water bodies, because we have modeled also this. So we want to incorporate sustainability constraint into economic production and see what could be the impact in terms of water use, or conversely in a dual version on production cost, if you want, and also assessing investment to improve efficiency in water use. Some future developments, this is the whole path we followed in building the model. We started with the regional model, then we included variability, and then we disaggregated at the sub-regional level. What we would like to do also is introduce some feedbacks in which, when in a region you get a given level of water stress index, you in some way constrain the output. So sort of output, supply constrained input-output model, but generated by the water resource. And finally, the final developments are, we want to extend the demand to water flows implicit in imports, because we want to estimate anyway the complete water footprint of Tuscan production. Tuscany imports water with inputs, so we want to model also this, and develop a water footprint analysis with structural decomposition by sectors and regions. We want to study the aggregation bias. What happens when you apply these tools at different scales, geographic scales, what you are going to be wrong, how much you are going to be wrong in using the not right scale, and extend the water footprint indicators to risks. We can model this in the literature. It is not so developed, this part. And finally, the final challenge is something that we talked a lot with Barbara, that is include generate the generation of water-related ecosystem service in the accounting framework and see what we can go forward, where we can go forward, and what we could find in using these typologies of models. Thank you very much.